So we want to do a hypothesis test comparing two population proportions. For instance, we want to compare the proportion of uh, males who go to Macy's to the proportion of males who go to a sports or outdoor sports place. So we want to make sure that the populations that we compare are independent of each other. For instance, let's take the example where we want to compare the proportion let's say we want to compare the proportion of males who go to Starbucks at the mall to the proportion of females who go to Starbucks at the mall. Now, by the looks of it, we may say, well, we have population of males and population of females, and males, females, they are completely different, and the populations might be independent. So here are the male and so even though we are comparing male proportion of males to proportion of females, we can't certainly say that the two samples are independent. For example, males and females go together as couples to the mall to buy stuff. So, if they go as a family thing, looking for clothes or looking for toys, whatnot, then the male is going to drive the female to go to the mall, or the female is going to drive male to go to the mall. So there is a possibility of dependence here. So here we would say no. But consider this example, the proportion of males who go to Starbucks at the mall to the proportion of males. To a proportion of males who go to Starbucks coffee shop. So clearly these two do not have a dependence between the two, because one group is focused on males going to the mall, the other is focused on males who simply go to the coffee shop, and the coffee shop is not associated with the mall. So the second case, the two samples here from the two populations that are the males are independent of each other. They do not have a relationship, they are completely separate entities. So when we perform a test, we've got to be very careful when we compare two population proportions. The samples from the populations must be independent, and this is typically guaranteed if the populations are independent. Then the samples are independent. Graphically, let's say we have two populations, and you can see that there is no connection between the two populations, and we collect a sample here, we collect a sample there. So that is sample 1, sample 2, population 1, and population 2. They are independent, so the proportions that we want to compare here are perfectly fine, and we could use a two-sample proportion test to find, to obtain, evidence toward a particular claim or otherwise. So things to note in terms of notation. So we call P1 to be the proportion of the first population. P2 is the proportion of the second population. P1 hat is the sample proportion obtained using a random sample. From the first population. And P2 hat would be the sample proportion obtained using a random sample from the second population. And I can't stress this enough that we want the samples to be independent of each other. They have to be independent samples. So how do we find the sample proportion? So first we want to determine the event of interest. For example, in our mole example, so for the first population, the event was males who go to Starbucks at the mall, and we'll call that X1. For the second population, we have males who go to Starbucks coffee shop, and that would be X2. So if I collect a sample of size N1, so N1 is the sample size of the first population and N2 is the sample size of the second population to be precise, I'm just going to add a number of males and number of males who go to a Starbucks coffee shop. So N1 would be the sample size, in other words, the total number of customers who go to Starbucks at the mall, and N2 would be the total number of customers who go to Starbucks coffee shop. So what we have here, P1 hat, would simply be X1 divided by N1, which is the number of males divided by the total number, and that is for Starbucks at the mall. And P2 hat would be X2 over N2, which would be the number of males divided by the total number of customers. And we have a Starbucks coffee shop. So how do we define the hypothesis? The hypothesis is, if it is a two-tailed test, our claim is that the proportion for the first population is not equal to the proportion for the second population. If it is a left-tailed test, we're going to decide that the proportion for the first population is less than the proportion for the second population. And if it is a right-tailed test, we make a claim that the proportion for the first population is greater than the proportion for the second population. Regardless of the case, we can actually rewrite it in an equivalent form as that. I'm simply moving the P2 to the other side. So why do we write it this way? The key thing to note here is quite important. So if we want to compare two population proportions, we actually test for the difference between the two proportions. If that difference is 0, like here, then there is no difference between the two proportions. But if it is not equal to 0, then there is a difference, and it could happen in one of three ways: that they are not equal to each other, or one of them is less than the other, or the last case would be one of them is greater than the other proportion. So our step 2 now is to choose the level of significance. It is chosen by the researcher, and keep in mind that alpha, the level of significance, is simply the probability that we make a type 1 error, which is simply probability of rejecting the null when the null is true, It is the same as saying probability that P1 is not equal to P2 when in reality P1 is equal to P2. So that is the probability of type 1 error, and typically we want to set it at 5%, 1% or 10%. So as we know from the other videos, there are two ways to come to a conclusion with a hypothesis test. One is the classical approach, the other is the p-value approach. Regardless, we need to find the test statistic. So this is the test statistic where the numerator is the difference in two proportions, and N2 is the sample size, of the sample from the second population, and N1 is the sample size from the first population. And here P hat is what we called the pooled estimate for the proportion. In other words, we kind of come up with an estimate that is common to both proportions, a reasonable value that is common to both proportions. And an important property of P hat is that P hat is always between P1 hat and P2 hat, but not necessarily in the middle. In other words, the pooled estimate could be here, or it could be there, or it could be right in the middle, which is why we say that it doesn't necessarily have to be in the middle, but it is a possibility. So what does the classical approach do? Once we find this test statistic right here, we compare the test statistic to the critical value. So here, the critical value is obtained using a standard normal distribution with mean 0 and standard deviation 1. In a TI-8384 calculator, the function would be inverse norm. We choose the area for the critical region, which is alpha over 2. Alpha is given in the problem, or would be given in the problem always. For example, if alpha is 0.05, that would be 5%, we would have 0.025 area there, 0.025 area here. And that would be 2.5% on either side giving us 95% in the middle. And we obtain a conclusion we'll draw it on the real number line. We have negative z sub alpha over 2, positive z sub alpha over 2. And if the test statistic falls somewhere over here, then anywhere between those two values, we do not reject null. For a left tail test, we're going to have the alternative that P1 is less than P2, or equivalently, we have P1 minus P2 is less than 0. We find one critical value, which would be on the left tail. The area that we use here would be alpha. For instance, if alpha is 0.01, that would be 1%. So we would have 0.01 area here, which would imply we would have 99% above that critical value. So on the real number line, the critical value would be right here. It will be negative because this is from the left tail. And if the test statistic falls anywhere over here, then we reject. And the last case would be to look at the right tail test. And for the right tail test, the null or the alternative is P1 is greater than P2, or equivalently P1 minus P2 is greater than 0. And a critical value here would be on the right tail. 0 would be right in the middle, and that critical value is going to be positive. In the previous case, it was negative. The area that we use would be alpha. And for example, if I said alpha is 0.1, that would be 10%. So the area above that critical value would be 10%. The area below would be 90% or 0.9. Now, we reject the null in this case. So 0 would be right here. That's the positive critical value. The rejection region is there. And if the test statistic falls anywhere here, then we reject null. The other approach is to find the p-value. The p-value would also need the test statistic, and we can, or I am going to show you how this could be done using the calculator directly. But if we want to find the p-value manually, we can find it depending on the test. So keep in mind that p-value is a probability. Specifically, it is the cumulative probability. And we need the test statistic to compute the p-value. In this case, we use the standard normal distribution. That is, the mean would be 0, standard deviation would be 1, and lastly, if we're going to use a calculator, this would simply be normal CDF. That is the function that we would have to use. So if it is a two-tailed test, we first find the test statistic and we add the area above the absolute value on the right tail and below the absolute value on the left tail with a negative sign, which is right here. Or, in short, we could write it as 2 times the area above the absolute value of the test statistic. So we have to find the test statistic, period. Now, if we're going to use the calculator, this would simply be 2 times normal CDF, the absolute value of the test statistic. Since it is area above, we start at the value of the test statistic, go all the way up to infinity and 0, 1. If it is a left tail test, the p-value is the area below the test statistic and if we're going to use the calculator, since it is the area below, we start at negative infinity, go all the way up to the value of the test statistic. So that would be normal CDF, negative E99 for a negative infinity, Z0, and 0 and 1. Similarly, for a right tail test, excuse me, the p-value is the area above the test statistic. Area above or area to the right of the test statistic, they mean one and the same. And if we have to use the calculator, we start at the test statistic and we go all the way up to positive infinity. And we know that this is a normal distribution, mean 0, standard deviation 1. So the p-value is simply normal CDF. Start at the test statistic, go all the way up to infinity, mean 0, standard deviation 1. And as I mentioned earlier, how do we reject the null in the classical approach? We compare the critical value to the test statistic. We have 2 critical values for a two-tail test. And if the test statistic falls in this region on the real number line or in that region, then we reject null. That would automatically mean if the test statistic falls here, we do not reject null. For a left tail test, the rejection region is on the left hand side and the critical value will be negative. And if the test statistic falls over here, we reject null. If it falls anywhere there on the real number line, we do not reject null. And the last case, The right tail test, the test statistic is on the right hand side. It would be positive because 0 is always in the middle. And if it falls anywhere there, then we reject null. Otherwise, we do not reject null. The p-value approach is typically easier. All we have to do is ask the question, is the p-value less than alpha? If you say yes, you reject the null. If you say no, we do not reject the null. But you do have to be careful that the p-value definition depends on the type of test. Which is left-tailed, right-tailed, or two-tailed. As always, the conclusion would be we reject the null, which would imply we found evidence if we do not reject the null, an economist believes that the percentage of urban households with internet access is greater than the percentage of rural households with internet access. So just by looking at it, we can say the percent of urban households with internet access would be our first proportion, and the first population would be urban households. The second population, or the second proportion, would be the percentage of rural households with internet access. So that would be P2. And what does the economist believe in? He believes, or she believes, or they believe that P1 is greater than P2. So we have to write the definition first, so let's go ahead and write that. P1 is equal to P2, that is the null. P1 is greater than P2, that is the alternative, that is the economist's belief. Or equivalently, we can say that P1 minus P2 is equal to 0 against the statement P1 minus P2 is greater than 0. And we always test for this difference. What else do we know? We have set an alpha. The value of alpha is 0.05. And we have some sample information. So the urban area would be the first sample. Rural area would be the second sample. And we have a total of 800 urban households. and 338 of them have internet access, and he observed 750 rural households, and 292 of them have internet access. So we can easily find the pooled estimate, which is p hat, and that is simply x1 plus x2 divided by n1 plus n2. 292 plus 338 divided by 800 plus 750. And if we put that in the calculator, we get 0.4065. And P1 hat would be x1 over n1, which is 292 over 800. And P2 hat is x2 over n2. And you can clearly see that P hat is 0.4065. It's right over here. And it doesn't have to be right in the middle. So the next step is to find the test statistic. Of course, you could go back and plug it in that giant formula, but I am going to use the calculator here. Go over to tests, scroll down. We have two prob Z test, and it is asking for x1, n1, x2, n2. So 292, 800, 338, 750. And we have to select the alternative. And we've decided that we have to do a right tail test. P1 is greater than P2 because that is the economist's belief. The person believes that the percentage of urban households with internet access, P1, is greater than the percentage of rural households with internet access, which is P2. So, of the three options, we are going to select option 3, which states P1 is greater than P2. Must have made a mistake somewhere here. It's 800. So the sample size has to be bigger than, x1. And if I calculate, we end up getting the test statistic, which is Z0, is negative 3.432, and the p-value is 0.9996, and you can see p hat is 0.4065, which is the exact value we had over there. The last step is to obtain a conclusion. So the classical approach compares the test statistic to the critical value. Since this is a right tail test, we need to find Z sub alpha, which is Z 0.05, because in step 2 we chose alpha to be 0.05. We find that critical value using inverse norm, and it has to be the area to the left of this number, which is the positive critical value. If the area to the right is 5%, the area to the left is 1 minus that, which is simply 0.05. We put 0 and 1. And we have 1.645. And that is our rejection region, the one that I just shaded. Now, where does the test statistic fall? The test statistic falls somewhere over there. So that is our rejection region. So if it falls in that shaded area on the real number line, we reject. Otherwise, we do not reject. So clearly, we cannot reject the null. The next approach is to use the p-value. The p-value that the calculator gave us was 0.9996. Now we have to ask the question, is p-value less than alpha? Is 0.9996 less than 0.25? In other words, is 99.96% less than 5%? If you say yes, we reject null. If we say no, we do not reject null. So clearly 99.96% is not less than 5%, so we do not reject null. So the null is P1 equals P2. The alternative is P1 greater than P2, and that was the economist's belief, and we did not reject the null. In other words, we are sticking to that argument. So there is no support to the economist's belief. So we do not reject null. Therefore, there is no supporting evidence toward the economist's belief. So even though we could find a conclusion using this approach, we could always find something called the confidence interval. So that is simply P1 minus P2. We can easily do this using the calculator. Press press start, over to tests, and scroll down. Option B, and we already have the values populated. X1 is 292, N1 is 800, X2 is 338, N2 is 750. The confidence level is 0.95. Because alpha is 0.05. Note, the confidence level is 1 minus the level of significance, so 1 minus 0.05 is 0.95. So when I hit calculate, the interval CI is confidence interval is between negative 0.1345 all the way up to negative 0.0369. So if you draw this out on the real number line, so 0 is over here, and the upper bound is negative 0.0369. The lower bound is negative 0.1345. In other words, the difference is going to be right here with 95% chance. So clearly P1 has to be less than P2, because the difference is P1 minus P2, and if P1 minus P2 is less than 0, which is the case right over here, because the difference is less than 0, it would imply P1 minus P2 is less than 0 and P1 is less than P2. And that would be our conclusion. But is that the economist's belief? No. The economist's belief is P1 greater than P2. What does the data tell us? The data is telling us that P1 is less than P2. So we could conclude the hypothesis, or obtain a conclusion for the hypothesis using this confidence interval, and say that there is no supporting evidence toward the economist's belief. So the point here being that you can obtain a conclusion to a hypothesis test using a confidence interval. So here we have to use the true 2 prop Z interval, which is option B under the start option in TR-84, and to perform the test we select option number 6.